I will now explain the origin of the coupling of the amide 1 oscillations on different amide groups. This coupling has its origin in the electrostatic interactions between the oscillating partial charges on the atoms. Figure shows a classical dipole, here, where two partial charges are connected by a spring. This is a simple model for the CO bond with a positive partial charge on the carbon and a negative charge on the oxygen. Let us further assume that one such CO bond oscillates, as illustrated on the left, and the second one is at rest, shown on the right. Then the oscillating charges of the left CO bond will exert electrostatic forces on the resting CO bond on the right that vary with time. In other words, the resting CO bond feels the oscillation of the left CO bond and is influenced by it. The oscillating forces cause the charged atoms of the resting CO bond to move so that the right CO bond starts to oscillate, while the left CO bond oscillates less, until it stops to oscillate and only the right CO bond oscillates. Subsequently, the left CO bond starts to oscillate and the right CO bond oscillates less, and so on. This phenomenon reveals that there is energy transfer back and forth between the two oscillators. We have encountered the phenomenon of energy transfer already when we discussed the vibrating tree trunk. In the tree trunk example, starting the horizontal vibration led with time to a vertical oscillation and vice versa. When the tree trunk oscillated in the horizontal direction, all oscillation energy resided in the horizontal vibration. Later, when it oscillated in the vertical direction, the oscillation energy was in the vertical vibration. Thus, there was energy transfer between the horizontal and the vertical vibrations because these two vibrations were coupled. Because of the energy transfer, none of these two vibrations was a normal mode. Instead, the two normal modes consisted of the two diagonal vibrations. There was no energy transfer between the two diagonal vibrations because when one of them was started, the direction of oscillation did not change. It turns out that the vibrational coupling between amide 1 vibrations of different amide groups can be described by coupling between the transition dipole moments of the amide 1 vibrations of the interacting amide groups. Therefore, it is named transition dipole coupling. As any interaction between dipoles, the strength of interaction depends on the relative orientations of coupled dipoles and on the distances. Therefore, the vibrational spectrum of the amide 1 vibrations depends on the three-dimensional structure of the protein backbone. This can be easily seen even with our simple CO bond models. In this situation, the two CO bonds align. To make our lives easier, we will discuss only the strongest interaction, which is the interaction between the closest atoms of the two bonds, which is the interaction of the negative charge of the left bond with the positive charge of the right bond. Negative charge of the left bond and positive charge of the right bond. We also discuss only the force that the negative charge exerts on the positive charge. This force is always attractive, but the magnitude of the force varies. It is stronger when the negative charge of the left oscillator is closer to the positive charge of the right oscillator, like here. What is important is that the direction of the force is always along the bond, and therefore it can influence expansion and compression of that bond. Therefore, we get a strong interaction between the vibrations of the two oscillators, which results in a strong coupling. Here we have a different situation. The two bonds are perpendicular to each other. Now the strongest force the left bond exerts on the right bond is perpendicular to the stretching movement of the right bond. This would be the stretching movement, and the force is always aligned in this direction. It has in this particular geometry no component parallel to the bond, and therefore it has very little influence on the stretching vibration of the right bond. Only a force component along the bond can influence its stretching vibration. This situation does not change during the vibration of the left bond. The force is always perpendicular to the stretching movement of the right bond. In this example, we have seen that we have strong coupling when the two CO bonds align, but weak coupling when they are perpendicular to each other. This shows that the coupling depends on the relative orientation of the two bonds. If these two bonds are part of a protein backbone, the coupling depends therefore on the structure of the backbone. We will now discuss the effects of transition dipole coupling in somewhat more detail. Transition dipole coupling has three effects. First, it delocalizes the amide 1 vibrations. Second, it changes the vibrational frequencies. And third, it affects the probability of absorbing infrared radiation. The effect of coupling on the infrared spectrum is strongest when the coupled oscillators vibrate with the same frequency. In other words, when they are in resonance. In a coupled system, we get as many normal modes as we have amide groups. However, not all of them need to be infrared active. We will first discuss the localization of the amide 1 vibrations. Infrared photons are absorbed collectively by a group of coupled amide groups, not by a single group. Thus, the excited vibrational state is delocalized over several amide groups. Delocalized excited states are also observed in other contexts and are named exciton. We will encounter excitons again in UV visible spectroscopy. Coupling interaction that generates the excitons is also termed exciton coupling. In the case we are considering here, exciton coupling is the same as transition dipole coupling. The delocalization of excitation energy means that each amide 1 normal mode consists of the local amide 1 oscillations of several amide groups. We have encountered the phenomenon of delocalization already before, when we discussed the vibrations of CO2. In CO2, two CO stretching vibrations couple, which leads to two normal modes with different frequencies. Each of these normal modes consists of both CO stretching vibrations, meaning that the normal modes are delocalized over the entire molecule. But the nature of the coupling is different for CO2 and the amide vibrations. Whereas in CO2, the two CO vibrations couple mechanically via the movement of the middle atom, the local amide 1 vibrations couple through space via electrostatic interactions. The coupled amide groups do not need to be connected by chemical bonds, or they can be very far away in the primary sequence. The second effect of transition dipole coupling is that it changes the vibrational frequency. Also, this is a general consequence of exciton coupling. It leads to a change of the excited state energies. Remember that the energy of the vibrationally excited states depends on the vibrational frequency. A change of vibrational frequencies can of course be observed in the vibrational spectrum. The change depends on the orientation and distance of the coupled amide groups, because this determines the strength of the forces between the oscillators. For two coupled amide groups, two different energies are observed depending on whether the local amide 1 vibrations oscillate in phase or out of phase. In the in-phase vibration, two oscillators expand and contract at the same time, and in the out-of-phase oscillation, one contracts while the other expands. The result of this coupling is a splitting of the excited state energy, and this is a phenomenon called exciton splitting. And exciton splitting is illustrated in this slide. Left-hand side, here, shows the energy levels of two isolated or uncoupled amide groups A and B. They are assumed to have the same transition energy, which is this energy difference, meaning that the amide 1 vibrations have the same frequency. Only one absorption band will be observed in the vibrational spectrum, because the transition energy is the same for both groups. The right-hand side shows the situation when the two amide 1 vibrations couple. Then we get two transitions with different transition energies. This is one transition energy, and this is the other one. The excited state energy is split into two energy levels, which are located symmetrically above and below the energy level of the isolated system. The two different transition energies imply that the coupled system has two amide 1 normal modes with different vibrational frequencies. Therefore, we will see two bands in the vibrational spectrum. Also, the phenomenon of energy splitting is familiar from the example of CO2. In CO2, coupling of the two CO stretching vibrations leads to two normal modes with different frequencies. Third effect of transition dipole coupling concerns the probability of absorbing an infrared photon. In other words, the transition probability from the vibrational ground state to the first excited state of the vibration. The two transitions on the left-hand side have the same transition probabilities. However, the two transitions of the coupled system on the right-hand side may have very different transition probabilities, depending on the relative orientations of the transition dipole moments. Thus, some delocalized vibrations may be much stronger absorbers of infrared light than the uncoupled vibrations, while other delocalized vibrations may absorb much weaker. We have encountered also this phenomenon already in the discussion of CO2. Each individual CO stretching vibration is associated with a change of dipole moment. But when they couple, only the antisymmetric stretching vibration absorbs infrared light, while the symmetric stretching vibration is infrared inactive. Now we can summarize this section on transition dipole coupling. This coupling is an interaction between the moving charges. The effects are the following. Several amide groups participate usually in a given amide 1 vibration. In other words, the amide 1 normal modes are delocalized over several amide groups. Transition dipole coupling changes the vibrational frequencies of the amide 1 vibrations. Some have a lower frequency than the uncoupled amide 1 vibrations, and some a higher frequency. It also changes the transition probabilities of the amide 1 vibrations. Some absorb infrared light stronger than the uncoupled vibrations, others weaker. All these effects make the amide 1 spectrum sensitive to the structure of the protein backbone.